I'm Pat Brown. I work for EPRI, the Electric Power Research Institute, and I am the moderator of today's second in the CIM and Network Analysis webcast series that's being sponsored by the CIM Users Group. I would like to welcome all of you back who were here last week and just say welcome to those of you who are attending for the first time. Like last week, this webcast is a replay of one that was done earlier in the day. And so while there will be questions at the end of the pre-recorded webcast that our presenter Chuck DeBose will answer as part of the replay, I would encourage you to also go ahead and enter questions of your own in the question area on that GoToMeeting pull-out window that comes out from the right. If you ask questions in writing, I will gather them together and we'll be setting up a kind of frequently asked questions forum so that all the questions from these webcasts are addressed. With that, let's go ahead and get started. I'd like to just overview our series here. Last week, Jay and Alan talked about the basics of power system modeling using the CIM. Jay talked about the 5 big facts of network modeling, and he presented the anatomy of power flow data through the eyes of the CIM. Then Alan shared information about how CIM models equipment and connectivity, which are sort of the foundational part of network model data. And he also gave us a tour of the support that the CIM has for diagram layout. Today, Chuck DeBose from Siemens PTI is going to walk us through some of the more complex constructs in the equipment and connectivity portion of the CIM. And then next Thursday, September 25th, Lars Ola Osterlund will talk to us about how the CIM supports power flow cases, how the steady state hypothesis, or SSH, profile describes the inputs to power flows, and the topology and state variable profiles support the outputs. And Jay will also return to give us a brief look at some of the current topics that are under discussion in Working Group 13, specifically model changes and model assembly. So recordings of all of our webcasts are available on the UCAI User Group YouTube channel, which can be accessed through the technical webinars link on the CIM User Group site quick launch bar. Last week's recording has been posted. And as a reminder, the PDFs from last week's presentation and this one as well, very close to the form that you're going to see them, are available at the Oslo meeting website portion of the CIM User Group website that is accessible by using the meetings link on the CIM User Group website. And one more thing, we are still working on consolidating questions and pulling together answers. My intent here is to consolidate the questions from all of our webinars and provide that, have our panelists provide answers to the entire collection of them once the webinars are through. My quick commercial. We would encourage you to attend the upcoming CIM User Group meeting in North America. It is the 11th to 14th, that's Tuesday through noon Friday, in Orange County, or LA, California. And as a participant in this webcast, you're entitled to a $50 discount off the early bird registration fee if you register before next Thursday, the 25th. I would just say that if what you hear today in the webcast is of interest to you, I think you would really benefit from attending the CIM User Group meeting. Not only will you get more in-depth CIM training during CIM University on the first day, but you can meet the presenters firsthand and hear all sorts of good information about how utilities are actually using the CIM in real-world projects. So back to today's webcast. It is on The more complex portions of equipment modeling, we're calling it steady state special topics. And Chuck's going to go over things like transformers, HVDC short circuit, dynamics models, and unbalanced modeling. With that, one thing I should remind everybody of, this particular kind of webcast, all of the attendee lines are muted, which means that we can't hear you talk. To submit questions, and we will have time for questions at the end of the webcast, you just enter them in the question portion of that pull-out menu that comes from the right, and I will see them and read them and pass them on to Chuck. So with that, I'll hand it over to Chuck, and could you just start, Chuck, by telling us a little bit about yourself, please? I'm now passing presenter over to you.
All right. Again, my name is Chuck DeBose. I spent 21 years at Virginia Power. They're now known as Dominion. They changed the name just as I was leaving the company. I had a little bit of time in some system protections and distribution engineering, but I spent the bulk of my career in transmission system operations. I worked actually in the operating center back when you actually did generation and transmission control before 2000. And in 2000, basically, I left and joined a little startup company, which was later bought up by PTI, and actually before Siemens bought PTI. So I've been away from Virginia Power for a little over, August, right at 14 years. So I've been working in the CIM all of those 14 years. I'm actually a member of Working Group 13 and recently Working Group 14. I work with the modeling subcommittee of that group. So that's basically my spend a little time talking about transformer models because it's one of the more complex items in the equipment model. HVDC, and this is brand new models been added in within the last year. They've been doing a little work with testing it at the last European interop. We talk a little bit about short circuit. I get some into dynamics. And we're going to talk a little bit about unbalanced networks, just to show you that there's capability within the CIM to model unbalanced networks. But the bulk of what we're going to talk about today is balanced systems. Within transformer models, again, this particular part of the presentation will be just on the balanced three-phase transformer model. We're going to talk a little bit about the tap changers, some of the voltage attributes. There's several associated with the transformer model. And I'd like to point you to a document for those in the European market or can get their hands on it. There's a NSOE, which is the European Union variation of NERC, which has produced a document on their phase shifter transformer modeling. It's out there on their website for those of you that can get access to that. Transformer models. Let's start beginning here. The power transformer in itself is a conducting equipment. Power transformer can be looked upon as almost a container to contain the individual parts of the transformer. And it's actually recently been elevated to a piece of, or a form of conducting equipment. The actual meat and potatoes of the power transformer on the balance side are the power transformer end and transformer end. As you see here, the power transformer end is the specialization or adds specialty or inherits, whichever term you're familiar with, to the transformer end. The transformer end is where the actual electrical connections are made to the terminal and internal the connectivity nodes. So the transformer end is what could consider to be a winding or the winding connection as far as electrical models go. The power transformer end actually contains all of your impedance data, your actual steady state impedances, and your zero sequence impedances.
Muted.
The transformer end you'll see later on is actually used in the Unbalanced also as a common piece of common element that can be used. Again, the power transformer end makes the actual electrical connections there. For instance, on a 230 to 115 transformer, there will be a power transformer again describing the 230 winding and its connection to a terminal to a connectivity node. And the 115 kV side will also have a power transformer end modeled with its connection to a terminal and connectivity node. In two-winding transformers, the impedances are always stored on the high voltage side. On multi-winding transformers, you actually store impedances in a star configuration on each transformer end. So just kind of give you a basis of that. Now, let's talk about the tap changer models. First, we'll get into a ratio tap changer. And to get your bearings, you have the power transformer end here. You can associate a ratio tap changer with each transformer end or every transformer end of the transformer if you'd like to do so. There are a number of cases where you actually have a regulating tap changer and a fixed tap changer on the same transformer, so that can actually be modeled. And for models that actually have a linear tap changer arrangement, you can actually slide a step voltage increment, which is basically a percent of the transformer ratio tap changer base voltage. And we'll talk about that here in a little more detail in a moment. And that basically inherits into tap changer. Now, tap changer is a dual-use class that can also be used by phase shifters, so we'll get into that here in a second. The ratio tap changer, again, defines just voltage step increment, actually a voltage control or voltage ratio change of the transformer. If you have a tap changer that's nonlinear, you can actually establish a table for each individual step or group of steps that and the actual ratio and impedance of that particular step, and tie that in. Tap changer also can be defined as with a regulating control. There's a tap changer control which inherits into the regulating control, which adds additional attributes which specialize the regulating control to be a specific tap changer controlling class. And that can also be tied to a regulation schedule, so that you can create regulation schedules for your equipment in your model. Again, all of this is considered to be in the equipment model or the equipment profile. And I think they'll be talking a little bit about profiles later on in this series. Moving on, phase tap changers, the other side of the tap changing model. Again, your transformer end to give you kind of a basis of where this is located. You can attach a phase tap changer to the, or associate a phase tap changer with the transformer end. You can specialize that in a number of different ways. There's a linear model which can be set up for a phase tap changer if you're just modeling a tap changer so that each incremental step in the phase shift is uniform across the whole tap range. You can also establish a table if you'd like, similar to the ratio side where each tap position has a different phase angle change, and also associate impedance changes with each tap. Over on the European side, they specifically use symmetrical and asymmetrical phase tap changers, whereas on the actual symmetrical side, you actually establish a trigonometry function. And then also there's also specialization if you have an asymmetrical type where you actually have a complex winding connection angle established on the transformer. Again, all of this again specializes the tap changer, which has a common set of attributes, stuff like high step, low step, your neutral step, things like that, are defined on the tap changer, and the tap changer can be associated with a tap changer control, which specializes in regulating control, so that you can actually set up regulating targets for this phase shifter. Again, regulating control can be associated with a regulation schedule, so you can associate a set of regulation schedules with each phase shifter. As I mentioned earlier, the transformer models have a series of different voltages that you can specify on the model, either the end classes or the actual tap changer, ratio tap changer class. There's a rated U on the transformer end class, and this is the nameplate voltage of the power transformer winding. You find this actually on your transformer test report or your nameplate, and this is used to convert the impedances from engineering units to per unit. So it's very important that that gets classified properly. On the tap changer, each tap changer is actually defined a neutral U, and this is the voltage at the neutral tap point. So with your tap changers, you define a high step and a low step and a neutral step. A neutral step is considered to be at neutral voltage. On the ratio tap changer, the step voltage increment has managed to survive as a percentage quantity, and that's the percentage of the I'm sorry, I actually classified this incorrectly. I had a longer statement in this. If you wouldn't mind scratching that, that's an error on this slide. It's not percent of rated U, it's percentage of the neutral U here. So that's, I'm sorry, I made an error in my scramble to get these slides ready. Like I say, the step voltage increment is always in the percentage of neutral U on the tap changer, not rated U.
Unmuted.
HVDC. Basically, we got rid of the old rectifier inverter classes. We added and replaced those two classes with a number of other classes in order to model in detail the DC equipment. This was to support online applications with EMSs and stuff like that, where the models tend to be a little more detailed than just a simple power flow representation of a DC equipment. So we basically added in DC switch classes, where you actually model the details on the DC side instead of just the rectifier inverter with kind of a black box in between. We've added a whole lot into the containment area, and a number of other specializations with DC terminal and actually this DC node also, and things of that nature. You can also associate certain specific AC equipment with the DC model, so that you actually encapsulate the transformer on the AC side, maybe any series compensators and things like that. And we also have specific models for voltage and for current source converters. Look here a little bit at the HVDC containment. And I tried not to get too sketchy here. You can actually look in, if you've got access to some of the UML that's available with the models, you can see a lot more of this. Actually, the 301 document has a lot more detail, but I tried to slim this down to what's needed for this particular course. Those of you who are familiar with the CIM, we actually have equipment containers for connectivity node containers, and they exist right now with the specializations of bay, voltage level, and substation as being equipment and connectivity node containers. On the DC side, we added some additional specializations or additional containers. There's a DC converter unit which specializes the DC equipment container. We also have the DC line, which is now an equipment container. We also have down on the equipment and conducting equipment, we've got the AC-DC converter and the DC conducting equipment. So you see how some of this stuff can tie back, so you can actually set up an equipment container of a DC converter unit and associate that with a transformer, or, I'm sorry, with a substation, or multiple substations in the case where DC line is actually located over several different substations. Connectivity. We had to make some changes in the model to kind of specialize and add some additional items to accommodate the DC side of the model. Up on the existing equipment level, we actually had to split out the terminal, and we actually made a common class or core class of AC-DC terminal, with the AC terminal being called terminal. We decided instead of changing its name, we'd leave it as is to minimize the effect of this change on the software vendors and those people who are writing documentation and whatnot, to kind of make this consistent with what it was, or at least lessen the impact of the change. Of course, the core terminal for the AC side is associated with connectivity node, topological node, and conducting equipment. But on the DC side, what we ended up doing is we ended up adding a DC-based terminal to specialize the AC-DC terminal, and this is over on the DC side. And we have two subclasses of DC-based terminal. One is a standard DC terminal, which you connect switches and lines. The DC line equipment would connect between the converter units. And we actually have a specialization yet for the AC-DC converter DC terminal, which is the DC side of the converter unit. We'll look at that here in a real quick minute. And on the other side, we basically added another layer of DC objects to match the AC side. So on the AC side, we have topological node, topological island. We've added in DC topological node, DC topological island to accommodate the exchanges as they exist today. There's also a specific DC node, and the connectivity here is it's pretty much the same as it is on the AC side. It's just we wanted a differentiation between the AC and DC, so that when you were looking at these models or trying to import them into your software, you sort of recognize what was DC and what was AC, along with a few other items. Moving along, the HVDC converter unit. We have a standard class which carries the balance of, well, let's say the bulk of common items between the current source converter or voltage source converter, and they, of course, are specialized by the current source and voltage source converters based on which unit is actually exists in the field, so that you can model those specific attributes to accommodate a very accurate or highly detailed DC line model. There's also an association from there's an inheritance. Let me start here first. From AC-DC converter inheritance and conducting equipment. And this is where the terms located to define the electrical connections of the AC-DC converter. And that points into the core terminal, so that you can point to one AC terminal and one DC terminal on the actual devices. In addition, of course, terminal actually inherits into AC-DC terminal. There's actually an AC-DC converter DC terminal, which specializes the AC-DC terminal, and this is the DC side of the converter unit. And this association actually points to that DC side. In addition, as I said earlier, you're able to encapsulate certain AC equipment and associate it with the actual DC model, so that you can actually model a transformer and, like I say, series devices or any tuning compensators. And you actually put a pointer or set a pointer or association from the AC-DC converter out to the terminal that's furthest away from the DC equipment to encapsulate all that. The next slide actually shows this. So basically we have the basic DC line model with this is a current source converter tied into the terminal, to a DC connectivity node, to a DC line segment. You could model switches in here or anything else you would like to model with multiple segments, and you can get into multi-terminal DC versus two-terminal DC, however that wants to be set up. In addition, you can actually model the series compensator or power transformer into this model so that you can associate all of this equipment in with the DC model itself. And what you do, how you do that is basically from the converter, you set the association, the point of common coupling terminal from the converter unit out to the furthest terminal from the converter unit to gather all of that equipment in associated with the DC line. So if both of them had this set of arrangement on both sides of the DC line, it would be similar on the right-hand side as it is on the left. So moving from that, short circuit. Basically, all the short circuit data in the we actually used IEC 60909 to establish all of the new attributes that were added in. I think within the last 2 years, I think we've got them all in to accommodate that IEC spec. And basically, we've set all that data in to the wires package, which contains all of the electrical equipment in the model located in the CIM. So your transformers, your generators, and things, those items within the wires package actually contain the attributes to support the short circuit data. They're covered by a separate profile, which means that you can actually exchange your equipment profile separately from your short circuit profile. So if you have some applications that are using the equipment profile, they may only be interested in steady state data, and that data is contained in that equipment model. And for those applications that are used in short circuit, they can use that same equipment file, and we can pass in the additional data specified by the short circuit profile, kind of overlay the existing equipment data. So you can add in your zero sequence, your negative sequence, and even if you'd like to, you could replace your positive sequence points if necessary. As a footnote, within the short circuit data, all of the positive sequence reactances on the synchronous machines they're considered to be saturated values for short circuit. And that's a footnote because if those people are used to also working in dynamics, that data has to be replaced with dynamics data for unsaturated values for dynamic simulation. Let me get a little bit in here, talk a bit about grounding, basically in the Peterson coil, and kind of introduce you to the mutual coupling class, and also kind of take a quick look at the fault package, which defines fault locations, stuff like that, so you can pass that information around to your neighbors or neighboring systems. Peterson coil, it's a brand new class we've just recently added. It also adds a bit of a nuance to the way that equipment is modeled and connected together. Pardon me, I've taken a little bit of a shortcut here. I have not modeled or specified all the specific class instances that you need for all of this. It's sort of a shortcut in order to get this on the same diagram. So we basically, let's just start over on the left-hand side. We have a power transformer, which the power transformer ends are connected to terminals, let's say up on the high side, and at the terminal you actually specify which phases are involved connecting that transformer to the actual connectivity node. So on the high side we have phases A, B, C. This could be termed as like a delta. And if you look on the power transformer end, you'll see a connection type. So we have a delta to maybe a Y ground, or let's call it a Y in this particular instance. So the low side transformer end connect to the terminal to the low side connectivity node, and its phases are A, B, C, and N. So at this point we have a floating neutral coming down to connect to the low side connectivity node. Proceeding still down in the vertical, we have an AC line segment connected by a terminal to that same L1 connectivity node, and it's connected by phases A, B, and C. Considered to be a balanced AC line segment model. All this is considered to be balanced AC. Also, at the L1 connectivity node, we have a ground disconnector that connects only via phase neutral to terminal to the L1 connectivity node. This is the ground that's pulled off the transformer and now connected into a network with other pieces of ground equipment. If you go on the right-hand side, there's also the same similar power transformer arrangement with phases A, B, and C connected to the low side of transformer number 2's connectivity node. You pull off a terminal to another ground disconnector, only connecting to phase neutral or phase N, and all that connects together through a series of terminals, other equipment, connectivity nodes, so you can establish an entire network of grounding here. If you want to bolt solidly to the ground, to a ground, you can actually specify that and attach a ground to connectivity node C1. You can set up other switches. You can set up an impedance device. Basically, you go through the CIM and find these devices. You know, a fault isolator, things that fault isolator, fault ground device, or a grounding impedance device. In this particular example, we actually have a Peterson coil attached to the C1 connectivity node via terminal, and with, again, its phase is set to neutral only. And this Peterson coil would then control the actual ground impedance that's available to these two parallel transformers. And this is in a situation where you have two transformers in the same situation where you have a common Peterson coil. If each one had its own Peterson coil, you define the network in that manner. But it gives you an idea of how this connectivity works and how this can actually be designed in your model. Mutual coupling. This is, again, display of the actual CIM standard and how it's organized. Basically, we have AC line segments inheriting into conductor and inheriting into conducting equipment, and that conducting equipment could have several terminals. In the particulars of an AC line segment, each AC line segment has two terminals, connect each end of the line. With a mutual coupling, you can have two AC line segments coupled together and define them in this arrangement. So in the particular model, you would actually have two AC line segments, each with its own set of terminals. The mutual coupling has an association to the first terminal. This first terminal association actually connects to the reference end of one of the AC line segments, one end or the other. So it's kind of a starting point for, say, AC line segment number 1 in the model. It also has a second mutual coupling that comes over to the reference terminal of the second AC line segment in that mutual coupling. Keep in mind this is also a reference from the same end, so that your distances that you defined in here are set to from the proper reference point. Well, next slide will actually show that detail. And then you also put in the impedances associated with the mutual coupling. Each mutual coupling is capable of being named, so it's inherited into identified object, which is kind of the footnote. Now, how does that apply to kind of real life here? Given the previous UML example we had, we actually have a mutual coupling instance. It has a first AC line segment terminal point to the reference terminal of the first AC line segment. Second reference terminal points to the reference terminal of the second AC line segment. So if you don't point to each end or both ends of the AC line segment, you pick a reference end for each of the AC line segments, and then your distances are calculated from that reference end. So, and I think most everybody that's worked in this environment has kind of worked at similar models. This doesn't drift too far away from what everybody's used to. The distance, 1-1 basically is the distance from the reference terminal to the point at which the lines are in close proximity, where your mutual coupling begins. Distance 1-2 is, again, the first AC line segment from the reference terminal to the end of the point where they're mutually coupled. Distance 2-1 and 2-2 are similar. They're calculated from the reference terminal of the second AC line segment to the point of where the coupling begins, and then of course the 2-2 is the endpoint at which the coupling ends. So pretty much describes what's going on with mutual coupling. Fault analysis, fault package, where you can actually define a fault at a location and actually give the fault impedances and whatnot. So basically, you've got a class that describes the fault, and it describes the impedance at the fault at this particular location, what kind of fault it is, whether it's line to ground, line to line, line to line to ground, which phases are involved. So if you've got a line to line, you can define this as a three-phase fault, A, B, and C, or an A to C, or a B to C, or whatnot. Same thing in the line to ground. You can find the different fault types. So you define your fault, whether or not this is a line fault or an equipment fault. You can define a link from terminal 1, and if you look on the AC line segments and the terminals connect to those AC line segments, there's a sequence number on the terminal, and that's actually the sequence 1 is the link from terminal 1, or defines terminal 1. So same thing, or similar on the equipment fault side is you can actually tie that to the terminal of a piece of equipment. So you can fault a breaker, one side of a breaker versus the other side of a breaker, or one side of a transformer, the other side of the transformer, whatnot. And actually, so from the equipment fault, make an association to the specific terminal of the fault location. You also can point the fault at a piece of equipment and define whether or not, I guess it's just more of an association in addition to the actual location. This association just says that you're faulting this transformer, we're faulting this, breaker. So more for informational purposes. And then we actually have a association out to identified objects, so we can actually give a fault cause type and define that. I think that pretty much completes this guy. Dynamics. I'm going to run through this real quickly. Actually, time's looking pretty good here. On the dynamic side, we looked at this and we decided that, again, we wanted a totally separate package external to the equipment model. Therefore, you didn't have to pass the equipment model every time you wanted to update the dynamics. It could be defined under a separate profile, nice clean separation. And then basically the equipment, the dynamics models actually have associations into the equipment they actually represent, or in the case of a generator dynamics model, you can point to the specific generator that this model refers to, represents. We've got very detailed models for loads and generators, and we'll talk a little bit at the end of this about where we would like to go with this package. And right now we're undergoing a very extensive vendor testing program, testing all of the vendors. We're doing this actually in conjunction with NSOE, the European Union electric system, and we've got several vendors involved in basically comparing results against one another. Now, let's talk about the organization of the dynamics package. Many of you that work or are familiar with dynamics probably looked at this and seen this diagram. And this is basically a standard package or a standard association of different devices or components within a dynamic simulation. You have a synchronous machine, and you have different dynamic components which represent specific devices or controls within the synchronous machine's control system that affect the stability and dynamic response of that machine to any perturbations on your system. You have signals that feed out of your electrical system that feed as inputs into these individual devices, and you basically have a setup or a model of something similar to this for every synchronous machine in your model. Some of them are very simple, some are very complicated. So instead of trying to tackle all of this and saying, hey, we've got to model this specific topology and show all these signals that run between the different models, we decided to take a shorthand view of this and say, basically specify, if we specify the models in this and the fact that they're standard using a standard connection, we do not have to define all this topology. So all we have to do is associate all of the different models with a specific synchronous machine. Then everybody in the world knows that, you know, if I've got a voltage compensator and exciter on associated with a synchronous machine, this is the way they're hooked up. Now, over on the CIM side, how that actually looks is in the equipment models, and this is only the synchronous machine side. We've actually got an asynchronous machine model also set up. So we'll walk you through the synchronous side, and once you get a handle on this, the asynchronous side is fairly, you know, duplicates or similar. Synchronous machine, again, this is specialization of rotating machine. That's located in the equipment model, so you can actually pass an equipment package around containing all of the steady state information on you know, for your steady state model without having to carry around the dynamics information. So you can pass that steady state model into your state estimator or your online power flow or your offline power flow or your planning power flows, whatever. And when it comes time to do a dynamics study, you can then pass in the dynamics data along with it, and then what you end up having is a synchronous machine dynamics class or instance, which carries all of the attributes necessary for that synchronous machine, and there's a number more that, you know, specialize into this. This is just the standard synchronous machine. There's several specializations of synchronous machine dynamics in the dynamics model to define either detailed or not so detailed generator models. And like I say, there's a single association that goes across to its corresponding synchronous machine in the equipment model. Now, what we decided to do in the organization of this, if you take the previous diagram and kind of work from right to left, that defines the hierarchy. So in order to have a turbine controller or turbine governor, or even a turbine controller, you must have a turbine governor to associate to. And that turbine governor must attach to a synchronous machine dynamics, and that, of course, synchronous machine dynamics must be present in order to hook into the equipment model. So that defines pretty much the hierarchy of all of this. And I simplified this a great deal because the original drawing is quite a little hard to follow in the context of a presentation. So I've removed some of the classes. There are more classes here to accommodate additional devices. And again, when you specify an excitation system, you know, using this model method, you're assuming that the signal inputs and outputs are just as they're shown on that standard document shown before. And there's several different arrangements of this that can be declared based on how this is defined. There's a standard arrangement for synchronous machines and a standard arrangement for asynchronous machines. All of these packages inherit in one form or another into a standard model's dynamics function block. And this is a standard function of its own. We also have a parallel model that you can use to define proprietary models. So if you've got a one-off set of software that defines a excitation system, you can define that and actually pass it along, or at least pass along notification along with the parameters associated with that, with the standard model, and then give some contact information of who needs to be contacted to get the specifics of that model. That way, if you own a model and you would like to, you know, it's got the copyright on it, you know, that copyright's maintained, and no proprietary information is exchanged with the standard data. Moving on from that, I was taking an example of an excitation system. And basically within the CIM, it's defined as simply as this. You have a specific exciter, and we're pardon the similar names. This is an exciter AXC IEEE AC1A, and here's a list of its attributes. And the fact that that inherits into an excitation system dynamics, the fact that you only have exciters that inherit into the excitation system dynamics. It's a similar structure for turbine governors and turbine controllers and voltage compensators and the like. And again, the excitation system ties or associates directly to the distinct machine dynamics. Again, shorthand method. You don't define the signal inputs. You don't define, looking at this, you don't really even know what this model represents. Within the profile, we've also stored, the actual internals of how this model functions. And this is the example of an AXC AC1A exciter model. So you can see you have your inputs and whatnot, your voltage, your compensated voltage, your system voltage, reference voltage, your high and low voltages if you have voltage limiters, and whatnot, and then the actual mathematics of this model and how all those individual attributes that you define in the EXC AC1A class and how they're applied into the equation and what decisions are actually made. Some of these models actually have decision gates on what kind of input. So if you have a voltage input or you have a current input, if you got a frequency input, and it could be one or the other based on how you want your model is designed, you can actually specify that based on the model type. So when you do get into some of those models that can take different kinds of inputs, those can be classified and specified actually on the instance of the model that you're exchanging. And of course, your output side, the fact that you're pushing the electric field value over into the generator system dynamics, and then pushing back or receiving back the current, the field current. All right, moving on from here. As I said earlier, we've been doing some dynamics model vendor testing, and like I say, if you're looking at these are the responses of certain model packages where we defined a generator to start with, and later on we had a generator and a governor, and the next one we did was a generator, governor, and exciter, that kind of stuff, kind of get an idea of how each person is able to transmit data or pass data from one vendor to the next, and the data can be received, put into their native simulation software, and then simulations output, and then producing basically a set of output curves, and we're basically exporting, I think it's 12 curves for different components, and for actually 3 different scenarios that we're studying. So in some cases, the vendors are all lining up very much together. In some cases, the output isn't so pretty, so we still have some work to do to figure out why some of these models aren't responding correctly. And all in all, most of this tends to be to come back to some representation or a slip in the conversion, so that helps us clean the conversion up, so we end up with the same response amongst all of us, so that if Siemens wishes to run a simulation and pass that off to another vendor, or another, let's say a Siemens user, can take basically the models and whatnot, pass them off to a neighbor who can use a different non-Siemens simulation software and get the same results, and compare results at the engineering end instead of down in the trying to say, well, this attribute really means this over in your software, type of stuff. So it's very good common ground here. We still need work here, though, basically in the DC, FACS, relay devices, and shunt compensator models. Been spending a lot of time on the generator just for the vast number of different models. It's taking a lot of time to go through and define each of those models, and of course we're still finding a few little things as we go through it, and the vendors are running their compare. Amazingly enough, it's not as many as we really thought there were going to be. We still need to complete the development on some way of defining user-defined models other than the proprietary. If somebody wants to make their model public, right now they'd have to run through a process and get that model standard accepted into the standard, which would be the most desirable thing to do, but we really should have some methodology for defining a user-defined model, which is going to be pretty complicated, because there you actually have to define the topology and how everything's connected and signals and whatnot. So we also have to deal with the future distributed energy resources, which are on the way in. We're seeing more and more of this with the solar and the tidal and some of these other devices, and basically how they respond to any form of dynamic stimulation. And I think there's work even within the dynamics world to get a foothold on that understanding. So we know there's more work left to be done, so things our work cut out, I guess. Unbalanced networks. I'll go ahead and finish up with this real quickly here, right on schedule. Basically, the foundation for the unbalanced networks is defined under the IEC 61970 standard, and it's further detailed in the 61968 standard for the distribution. Most of the equipment attributes and whatnot are contained up in the 61970 standard. We also have classes added here, to define the individual phases of an AC line segment, switches, energy consumers, and so forth. So we basically duplicated the three-phase balance model with an individual phase model, so you can define an implementation where you have two phases instead of a full three-phase, or even a case where you may have three-phase, but one of the phases is you use a larger wire. Or in the case of transformers, you can actually have unbalanced transformer banks, where you have cases of a small grocery store or a grocery store gas station type of installation. You don't have to have a balanced three-phase transformer model. You can actually model the fact that it's an open delta with one transformer being larger than the other, and actually model that in specific detail. And you can also design and model single and two-phase circuits for overhead and underground installations. On the transformer side, just a real quick run through here. This is a particular situation of an open delta where you find installed all over locations and distributions. And actually, you'll find these installed in substations, providing local power to the substation. You'll generally find two tanks configured in an open delta. One of them connected on the primary side between A and B, the other one between A and C phase, and then the low side connected to the S1 and 2 versus S2 and 3 neutral terminals on the low side. And this is done kind of as a less expensive implementation of a full three-phase balanced transformer installation. Now, going back to the UML, I also introduced in to that first UML drawing I showed up in the beginning of this presentation, where your power transformer and transformer end, instead of actually having the power transformer end where the impedances are located, you now have a transformer tank end that defines which phases are included at that in that transformer end. The transformer tank end, specialized on the transformer end, is actually similar to the power transformer end defined earlier, except for you can now define which transformer ends are in a given tank and what phases they represent. So you can go back in and say that a single tank is connected from a primary terminal to a secondary terminal, or from terminals AV on the high side to the other transformer end, being S1 and 2 in that previous diagram. And of course, the transformer ends are contained within a tank instead of a power transformer. So therefore, you can organize this as is actually built in the field. The impedances are not stored on any of the classes associated with what we've described here. They have to be stored externally, and you can store those in two forms, either via a mesh arrangement or a star impedance. The star impedance basically has one impedance class or instance per transformer end. You define the impedances for that specific transformer end in that instance. Whereas the mesh impedance you defined or define those from one transformer end to another transformer end, and that's the impedance between those two transformer ends. And you basically use those with two different associations. So you have an association to I guess you have the first one goes to the from transformer end, whichever transformer end that might be. Let's say the primary side, and then the two transformer end could be the secondary side. And then you basically list the impedances basically from that terminal to terminal, if you wish to go, or transformer end to transformer end. You can also associate a core admittance with the transformer end and store the admittance values for that transformer. On the AC line segment side, as far as defining an unbalanced model, I think I'm going to save you on this one. I'm not going to actually get into the UML details of all of this. But essentially, what you have here is you've basically got connection into some three-phase system. Let's call it the low side, or the bus, a main bus in a substation, or even a three-phase line or a three-phase feeder that's coming out of a substation. And you've got all three phases represented connecting through to a connectivity node. This is kind of a shorthand representation. These phases are actually specified on the terminal connecting to this, this connectivity node. But in this particular case, we have a terminal connected to a jumper. And on the terminal, you specify that you only have phases A and C connected. Here's where it gets a little bit strange in the way that the distribution systems can be connected up. We actually are classified two different switch phases. One switch phase, and this is considered to be an actual switch, right? So it's an actual subclass of the jumper, connects phase side 1, which is terminal 1, this is your sequence, A phase to, and its side 2 terminal actually connects to B phase. So you have a cross, sort of a crossover. So you're literally connecting A phase on one side to B phase on the other side of the switch. Correspondingly, on the other switch phase, we're going to do the similar thing, is connecting terminal 1's C phase to A phase on the other side. And of course, terminal 2 has phases A, B specified on the outgoing side. This is how you can actually define that crossover if need be. And you have an AC line segment that connects from one terminal, let's say connectivity node, to another connectivity node, where you're carrying phases A, B out on a two-phase line that goes off in a direction. And you actually have a phase conductor out here, so you can define if these are two dissimilar conductor types. If they happen to be the same conductor type, they can be defined in an AC line segment. And the fact that the terminals are specifying that both ends are connected only to A-B phase. Single phase environment of this, or the equivalent of this, is down the B side. You're connecting an AC line segment with terminals B on both ends of this. And you can get into any variation of this you would like. So you can actually get down into specifying the conductor, and then actually define the geometry of how these conductors are set up on a pole. And that pretty much concludes my presentation. I actually finished a bit early.
Congratulations.
Yeah, I was actually concerned I was going to go a little over.
Doing better than the rest of
by talking fast. I hope I didn't push it too fast.
Oh, it's great. I have to say, though, it felt a bit like trying to sip from a fire hydrant. It was lots of good information, Chuck.
Thank you.
Thank you. All right, so we have a number of questions which have come in, and I will start through them. Chuck, I just want to let you know that you'll be ready to back up on some of your slides, because I think you may want to do that as you answer some of the questions. And I also do have a copy of the CIM XML up in Enterprise Architect if we want to actually go through and do some real referencing of the UML as we address some of the questions. So, in the order in which they came in, can you specify a table for asymmetrical ratio and angle? And we were back on the basic transformer tap changer model when that question came in.
Yes. Bring this up full slide. Again, speaking so fast, I may have just glossed over this without going into detail. This is the ratio tap changer side, and there's a corresponding table over on the phase shifter, or the phase tap changer side also. And you basically underneath, instead of populating the voltage, step voltage increment as a constant value, you can associate a table where you can actually define the ratio for each step and then its impedances for each step through that in nonlinear. So, step, 1 would have a specific ratio. Step 2 would have a different ratio. So you can actually define this table for each and every step through the full range of the tap changer. And again, correspondingly over on the phase tap changer side, there's a similar table. And that actually, instead of using the ratio, a tap changer table point, you actually use the angle here for each table point, and then its corresponding step and impedance quantities, and just leave the ratio quantity in the tap changer table point is null for the phase shifter.
Great. Okay. Next question. What is the correct place for connecting a three-phase grounding reactor to a neutral tree phase point of an autotransformer? Not the zeroth sequence. Wow, I'm having a hard time reading this. Not the zeroth sequence current flows through the reactor, but the first sequence flow 2.
So basically a series reactor or a series capacitor, God forbid. Pardon me. So in case of, let's say, a series reactance, that actually is, and I don't have that displayed here any, but there's a...
Do you want me to show UML? Would that help?
Yeah, the UML up, and we can actually...
All right.
Presenter.
So yeah, I just snagged presenter, so you guys should be seeing my screen with UML on it. Is that looking all right?
Yeah.
Okay.
Let's expand the wires package. We may actually have a... I think... Yeah, they don't have a picture of this, which is what I was kind of hoping for. But there's actually a... scroll down here a little bit.
Okay.
We have to be... I think it's series compensator is actually what it's spelled, so let's get the S's.
Let's see, yeah.
Yeah, there you go.
Okay.
That's the class that actually do this. So it looks like a series device, like an AC line segment or a or a transformer or whatnot. So you basically would have your power transformer connected with phases A, B, and C at the terminals, and on one side, to the other side of the connectivity node, you would have a series compensator with its individual attributes, the necessary attributes filled in, with the series reactance and whatnot. This would be the class you'd use. And you see these out on lines, you see them in substations, however they need to be. So you can define both the series reactor or a series capacitor. Hoping that properly describes what you're looking for.
All right. Is it planned to incorporate into the CIM wind parks and wind units suitable for dispatch or training simulator? Specification of IEC for modeling at time intervals up to 30 seconds is not enough. The wind speed should vary, for example. So I think that's a reflection on the use of it by DTS.
Yeah, there's actually another, that's a good question. Wind models are still being fleshed out, and actually there's there's other groups other than Work Group 13 that are working on some of these wind modeling systems. We've got hooks into our system of defining several different kinds of wind machines. As far as the defining wind over a long period of time, yeah, the dynamic side really doesn't cut this. It's actually a shortcut on most wind machine, or on most generators, describing inertia and a few other items. And I really haven't looked into anything that would be needed additionally on the wind side. I know that again, there's a lot of stuff coming in that we know there's need for, and this ought to be something we really ought to add into our to-do list. Pat, if you would mind.
I will take a note of this, the non-dynamics modeling of wind.
I don't, that's not only, it's long-term. It's
right.
What's being asked for here is basically almost a similar model that we do on load type modeling, where you'd model load over a period of time. You would also model wind. But maybe this comes up through the weather package.
Oh, interesting. Okay, so but non-dynamics is the point of it. It's longer-term behavioral modeling of, yeah.
Yeah.
So,
in simulations, you're really talking long-term, things that are, we always used to say in operations that you pretty much don't have any, unless it's automatic, you don't have any kind of operator ever intervention anywhere for upwards of 10 minutes. So, yeah, so you need to have that kind of time consideration here.
Got it. Good. I have made a note. All right, Chuck, I'm going to switch presenter back to you, because the next question is, does the simulations shown on slide 24, are they done in CIM or other tools? So it was your dynamics response.
It's 23 or 24. They're actually, the simulations are done in native tools. They're, I don't know that there's, well, there is no single CIM dynamic simulation tool. The CIM is basically a data transfer standard. Some vendors have chosen to use the standard as actually a form of containment, or let's say a basic design of the containment that they've organized. But when you actually get into the simulation software, you're taking those CIM attributes and that CIM structure and that definition, translating that into your native software. And each vendor then runs a simulation and publishes the curves. Or his curves, and those curves are, then combined on a single graph.
Perfect. Okay. I'm not sure how to interpret this one, but just let me read it. Can we think CIM in the transient state also? I don't know if it means outputs.
Could be. The transient state, of course, as far as we can go is into the dynamics. I think there may be some additional transient work that can be done, but right now only into the, I don't know if you call this large signal or, this is pretty much defining all the subcomponents in this. I'm not sure how to take that question really more than what I've already described in the presentation. Because what we're actually doing is based on some form of event on the electrical system, a fault per se, or even a switching event. You can model all of the individual control components and basically their response, the mathematics behind their response to that simulation. And it's, that can all be modeled. The event itself is described externally so that the people who run the simulation understand how how to run the simulation. But what we're handling here is the massive amount of model data that's got to be transmitted, whereas a short paragraph will define what how the event is to be established. I hope that helps.
All right, and we're kind of back on the same topic again, and the question is just wind power modeling specifics in CIM.
We actually, back to that UML that you'd shown earlier, I don't know if we need to go back there, that we do have some basic wind models, and it falls into the 4 different types and how they're, there's 4 different categories of machines, so where you have individual AC machines, or you have DC machines through some kind of converter, DC to AC converter, or you have a group of machines that may be DC feeding a single, DC to AC converter. And there's 4 different classifications of that. And that's as deep as the model. And pardon me, I don't have the IEC spec number, but there actually has been a group working on that. Pat, do you recall that number?
I was just looking for that as you were speaking. Yes, it is IEC 61400-27-1.
Okay, so there's work going along on this. There's a lot of these turbines have gone in. A lot of work has been going on lately trying to simulate all that needs to be done and include all of what needs to be included in these models. And there's more yet we have to learn, and there's more models beyond the wind. Again, some of these real small energy producers that have got to be defined in the CIM and transmitted and studied.
All right. We're finally off the topic of wind. Next question. Is there any facility in CIM to include XR ratio for calculating the fault current contribution and to characterize any fault injection from any part of the network? Is there any equivalent representation available in CIM?
Yes. Let's see where that is. Let's go look at the short circuit side of things.
All right. You want to switch back to the UML?
Yeah, let's go back to the UML. I had a moment for this. Because they actually did add some equivalent representations. It may take a second to find that.
Here's the main protection. No.
I'm not sharing yet. At least not coming out on my screen.
Oh, you're correct. I have one more click to do. Sorry.
Yeah.
Do you know what? I went to the protection package, but is that where it truly is?
No, it's not a protection.
No. Okay.
Still not seeing your screen. Might be I'm slow. I hope not.
Well, I am supposed to be sharing my screen. It says I am.
I see your screen, Ben.
Okay, perfect. Thank you, Jay. All right, so this doesn't help Chuck much, though, because he was going to try to drive this. Jay, do you know where I should be going to get to XR ratio for calculating fault current information?
No.
Yeah, well.
I need just a minute. I'm starting enterprise architecting.
Okay, very good. And I apologize.
I wonder what the deal is. This, or why I can't see your screen. Maybe it's only good for a certain number of switchovers.
Shouldn't be.
Hey. Oh, there we go. Well, just slow. No, it's not in the protection package.
Okay.
Let's short circuit. Let's try the equivalence. Let's try equivalent injection first, if you don't mind. Expand that.
Can you see it over there on the right?
Yeah.
Okay, or it's here, either one. certainly, we're going to collect together the questions and the answers and get them all published, and we can sure take this one offline and address it in that fashion if you'd like.
Yeah, I mean, just a quick.
All right. I tell you what, Jay, since you're on the line.
I found it.
Okay. Well.
It's actually called an external network injection.
Okay.
It's a class that's with, similar connection or connection capability as any other piece of equipment. And at that point, you can actually define let's say the available fault with all its X star or R and X ratios at a specific boundary. So you can define these at each boundary location of your network. So instead of dealing with an entire model trying to calculate the available fault coordinates local spots, you can basically donate a whole lot of a specific portion and replace the perimeter with those external network injections.
Cool. And here's the class and the diagram.
Was that developed specifically for short circuit, Chuck?
Yes. That's pretty much so. The reason I was stalling a little bit with this, it bounded around a little bit, and some equivalents and some things like that. It ended up here at this external network injection. They also, I think they tried taking the energy source and using that type of thing, which we had to shuffle it back, and so we ended up with this specific class to accommodate this.
Okay, the next question is how to model different running arrangements of substations in CIM. And I'm thinking that this is a containment question.
Ask that question again, please.
How to model different running arrangement of substation in CIM.
All right.
Or, never mind, go ahead.
Well, according to how this is interpreted, we're talking about the different representations of the same substation. There's an upcoming call which Jay is very familiar with in the series that will be talking specifically about that.
Yeah, I would have interpreted this more as switching, since it says running. Or
yeah, you're right.
Okay, so if you're talking about the same substation where you have a static layout, series of a number of transformers, AC line segments, switches, disconnects, connected together in a static layout that's unchanging as far as the layout itself. And actually, I think Larzola next week will be talking about this and represent PowerFlow. Was that last week?
No, that's next week. You're exactly right. Yes, and if that's the different running arrangement.
Yeah, the different running arrangements are the point of representing a condition where, line 1 connected to the following switches is out of service and switched open by these switches. That can be arranged for PowerFlow purposes or even as outputs to another simulation program that can be represented, with the actual device statuses for different time points. There's also regulations. There's also schedules that can be employed into the actual set switches open or closed.
Yep.
Necessary. Jay, does that kind of handle?
Well, that's the way I would have interpreted the question, is that basically if you have different running arrangements you want to model, you should model the switching that puts those in place.
Yeah. So you would model that station in explicit detail with all the switches and disconnects and every piece of equipment that's located in it. So if you were to mark certain switches as being open, they would disconnect the appropriate devices and such.
Great.
Oh, and one other thing to mention is that, which will be covered a little bit next week, is once you get the switches in place, you could save configurations for different running arrangements.
Correct. Yes.
All right, next question. Are some of these classes not in the IEC CIM 61970 yet? Faults, AC-DC terminal, etc.? I see them in version 16 of CIM, but not version 15. And 15 appears to correspond to 61970-301 edition 5.
That's profile publication and whatnot. Yeah, you're exactly correct. Those are brand new classes to CIM version 16. Basically 14, 15, and 16 represent changes that basically have been noted. It's solely by the European Union, but for their data transfers and whatnot, we've gotten into, let's say, some more specific modeling. None of this is to be abandoned by the U.S. or in the U.S. or any other part of the world. It's just a much more detailed representation of what was already there. In some cases, we had to displace things that there's just no way we could model an item appropriately. So we had to actually, remove instances or classes and install new classes, to replace them in order to accommodate these modelings. In addition, the distribution folks, 61968, had some additional needs that you couldn't describe properly in the CIM. So there are subsequent publications which have either been finalized or being worked on right now to describe 16 and will be upcoming 17.
And I would just like to point out that always our IEC documentation lags a bit behind the work we're doing. It is based on the CIM UML model, but all of the IEC standard documents that come out also have additional information, additional interpretation information in them. So the IEC standards themselves are, the biblical complete information about the Common Information Model, but that CIM UML model is a very good reference as well. The CIM UML is actually owned by the CIM users group, and if you are a company or an individual that's a member of UCAI users group, then you have access to what the CIM working groups have created as the last consolidated model that covers 61970, 61968, and 62325. So that full model, the most current combined version of it, is available on the CIM user group website. If we were on the home page, we could click on the current CIM model drafts quick link. And as long as you're logged in as a member of UCAI UG, you have access to the most current UML models, which is a place you can go to get more current information. Okay. Is there any different class for calculating fault current in the British standard G74?
I'm not familiar with that standard. I don't know how that equates into the 60909 IEC standard.
All right, so one more then. Do we have any solid CIM sample models in XML that can be used for reference?
I don't know if there's anything in publication yet. I know that the European Union, again, is working on several standard models. I know that the IEC profile documentation actually has examples, short examples. I may not contain the entire file, but they, based on what section you're reading, they've got examples within that shows the XML. And that's pretty much as far as I could go. It would actually be, you have to EPRI and CIM user group maybe to look into that.
That's a good.
I'm sure.
Yeah, I know that Alan McMorrin has created the IEEE 40 bus model or something like that, and probably he might be a source. certainly folks at NSOE during the interop dealt with a whole collection of solid some XML models, but I don't think they would be public. But you know what? I will make a note of that as well as something that might be of value. All right, I have another question that came in. Is there any way to transform the transformer model that as it exists in CIM 16 to previous CIM versions? And that, of course, wouldn't be a question for transforming to CIM 15, but it would be if you were going back to 14 or 13.
Yeah, there actually is. And it's, I don't know that there's too many attributes that are dropped, but there's, you might have to do a little fuzzy work as far as a couple of attributes that we did drop in order. Some of the cleanup work that went on the transformer was to remove some of the duplication, but yet keep the let's say the granularity of control. If you look at the transformer model, let's say just take the tap ratio model, you can actually have several transformers using the same regulation schedule, and you have the capability of let's say deselecting the control at the regulation schedule level or at the individual tap changer level. So you can actually turn a tap changer on or off. In the old model, some of those capabilities were were a single attribute that defined, this is a voltage tap changer or a voltage regulation schedule or a phase regulation schedule, or you're controlling current flow or voltage, or you're off. So when you set that attribute to off, you didn't know whether that transformer even had capability of regulating. It was just, connected in, but, and didn't know really what type of control it was. So, yeah, we've made some improvements in there, but capability going backwards, I think it's pretty much there. The core data is, moved around a little bit. The class names have changed up a little bit. Maybe some of the attribute names, but not to where it's unrecognizable. So you could go back to 15.
Good. Okay, a couple more questions have come in. How does the CIM manage proprietary dynamic models? For example, what if we wanted to do HVDC proprietary dynamic models?
The HVDC right now, the structure's not there yet, but HVDC will be handled similar to the other dynamics models. And I didn't show this in my slideshow. I actually mentioned it. Let's zip through it. That's probably a good diagram to go to. Doesn't get too busy.
So this is the proprietary dynamics, the support for how one can pass value, the generic mechanism that can be used for passing multiple parameters that are part of any type of particular dynamic component, so that you can define a dynamic component like an excitation system and then put as many parameters on that, not defined publicly anywhere, but you're saying parameter 1, parameter 2, parameter 3, parameter 4, and if both the sender and the receiver agree on what that ordering of parameters is, you could pass the information related to a given type of component. So that's what this ugly, spidery picture is about.
Yeah. And actually, if you go over what you'd end up having, there's another diagram that's kind of similar to this. You don't know. Let's also try to expand the excitation system, easier to find.
Okay, and the examples aren't a bad place either. Yeah, we'll do that.
Yeah.
Okay, standard
I'm
goals.
too hung up trying to dig around, find an item. Try the excitation system dynamics. The second one.
This one.
I think is actually probably the better picture.
Because it will have user-defined models here that are inheriting from it, so you can specify you can create an instance of a user-defined excitation system model. And then I wanted to flip down here to the examples. So this was the way that a dynamic model, fairly simple one for a synchronous generator, could be defined that had a proprietary turbine governor model in it. So it's a standard excitation system, a standard synchronous machine model, but here's the turbine governor, and it's proprietary, and you're passing 4 specific parameters that the sender knows about and the receiver knows about.
Exactly. So like I say, if you got access to the UML, this is a good place to go look. And basically what you're doing, similar to what's going on with the standard models, is you're just declaring the fact that this is a proprietary, non-standard model, and you need to go talk to the sender of what he used. You literally can get into the point of you wish to purchase this thing from him, or just to say the fact that, well, this is pretty close to an XYZ style turbine governor. You can use that in its place. For my simulations, I wanted to use something a little more detailed and whatnot. So that kind of work goes on today, and even you get to the point where you might say that, I've got it's a real special one-off turbine governor. I had to model something completely different from the standard models. Let me send it to you. And you kind of bypass the SIM exchange.
But you can still exchange the actual parameters even though nobody else might know the behavior model that they apply to.
And you may have this in 5 different locations where you just hand you one piece of simulation software, and you've got the full parameter list with your model exchange.
Great. Well, since we are now 3 minutes past our stopping time, I think I will wrap that up. We have a couple more questions that are outstanding, but I will make sure that they get included in our collection of questions. And I want to thank everybody for their attendance, and look forward to talking with you next Thursday on the 25th at the same time.